Welcome back. In our last video, we evaluated the expansion of cos 5 theta. This time around, we want to evaluate cos raised to the power of 5 theta and see what the result will be. Now, there is a lot of comparison between both expansions. The very first is that in the case of the expansion of cos n theta or sin n theta, the end goal is always to rewrite it in terms of power representations of the cosine or sine function, as the case is. That's cos cube theta, cos square theta, cos raised to the power 5 theta, and so on and so forth. However, when we evaluate cos raised to the power 5 theta or cos raised to the power n theta, as is the case here, our result will be in terms of the multiples of the angle, which is you'd have cos 2 theta, cos 3 theta, cos n theta, and so on and so forth. This, of course, becomes the very, very big distinction that exists between both of them. Now, in order to solve this, we still will utilize the expansion model that we already know. Remember that we have said that for cos raised to the power of n theta, we can simply expand it as 1 divided by 2 raised to the power of n, z plus 1 over z, all raised to the power of n. Similarly, so this would mean that if we have cos raised to the power of 5 theta, this will simply be 1 divided by 2 raised to the power of 5, z plus 1 over z raised to the power of 5. Now, all we just have to do now is to expand this bracket z plus 1 over z raised to the power of 5 binomially. As such, we would see that it will simply just resemble the same process we started for the last case, but this time around, unlike the other one where we expand in terms of cos and sine, this time around we are expanding in terms of z and its reciprocal. So how do we proceed? Same thing. For this, the expansion would simply be z raised to the power of 5 plus 5z raised to the power of 4 multiplied by 1 over z plus 10z raised to the power of 3 multiplied by 1 over z squared plus 10z squared multiplied by 1 over z cubed plus 5z multiplied by 1 divided by z raised to the power of 4 plus 1 divided by z raised to the power of 5. And we are done. So if we simplify this expansion, we would have, now it is very, very important to realize what exactly is your end goal here. When we simplify this expansion, we are going to have, for the bracket, we are still going to remain 0 raised to the power of 5 plus 5z raised to the power of 3 plus 10z plus 10 into 1 over z plus 5 into 1 over z cubed plus 1 over z raised to the power of 5. So what do you notice? From this process, you notice that by coefficient, you are simply going to have pairings of z and their reciprocal in terms of their powers. So in this regard, we can say that cos raised to the power of 5 theta would simply be 1 divided by 2 raised to the power of 5 into, if we take the first pairing, 0 raised to the power of 5 plus 1 over 0 raised to the power of 5, that is these two, then plus 5 into z cubed plus 1 over z cubed, that's the second pairing, then the last one plus 10 into z plus 1 over z. So we notice that 3 distinct pairs occur from this expansion. Now remember that since we know for a fact that cos n theta is simply equal to 1, of course, in this case, for all of them, you have this to be 1 over 2 into 0 raised to the power of n plus 1 divided by 0 raised to the power of n. If you are wondering why we know or how we know that this is completely true, you can check, of course, from the last expansions we did, and try as much as possible to add 0 raised to the power n to its reciprocal and see that you'd exactly have this. This would mean immediately that 2 cos n theta, of course, will be equal to 0 raised to power n plus 1 over 0 raised to power n. Which means if you adapt this for each of the brackets, then we would have some very, very interesting notations. Thus, we would have that cos raised to the power of 5 theta will be equal to 1 divided by 2 raised to the power of 5 into 0 raised to the power 5 plus 1 over 0 raised to the power 5 would simply be 2 cos 5 theta. Then this one will be 2 cos 3 theta times 5. That will be 10 cos 3 theta. And then on this side, z plus 1 over z, of course, would give you cos theta, 2 cos theta. So multiply that by 10, you're going to have 20 cos theta. So this is, of course, our expansion form. If this is the truth, we can, of course, factorize 2 out, so that we'll be left with 1 divided by 2 raised to the power of 4 here, multiplied by cos raised to the power 5 theta plus 5 cos 3 theta plus 10 cos theta. And this would be our expansion for cos raised to the power 5 theta. Of course, you can evaluate 2 raised to the power 4 as 16. You can also decide to expand this out and see exactly what you have. But this shows you how we can evaluate and transform the power representation of the cosine function into the cosine of the multiples of the angle. So this conversion holds true and it's vice versa. In the first example, which we showed in the last video, we went from the multiple of the angle into showing the power representation of the trig function itself. This time around, we start from the power representation of the trig function and end up with multiples of the angle. So this shows you that with the use of the De Moivre's theorem and the applications of the De Moivre's theorem, you can convert and expand various trig functions without having to use nominal methods like the additional factor formula or utilize multiple angle formulas, which are very, very common in calculus text. I hope this has been very, very clear for you. As practice, try as much as possible to expand sine raised to the power of 5 theta and see what the result would be. I would look forward to hearing from you in the comment section what you end up getting from that expansion. As always, make sure to like, share, and subscribe, and turn on your notifications so that you don't miss any of our videos.